For this training video, we will study about the hospital room. So, using the SolidWorks Flow Simulation 2012 tutorial, which is also applicable if you are using the latest version SolidWorks 2020, you could also as well use this manual since the examples are still the same. So, let's go to the D2, which is the hospital room. So, let's find it. Okay. So for this example, we will study about heating and ventilation. So we will be able to demonstrate using flow simulation on how to predict the performance of a building ventilation and estimate its air quality and the general thermal sensation by calculating comfort criteria. So first is we will open our SolidWorks model using the SolidWorks core program files folder and go to your flow simulation and copy the hospital room to your desktop. So in order to have you a separate file where when you are doing simulations. So once we have opened the file, we'll be able to see this model, the room, the bed, caregiver, the patient, and the fluid volume. Okay. So in this model, we have already the main, which are the patient, the caregiver, and the hospital room. So as part of our heating effect, we have the ceiling lights, hospital equipment, TV set that will affect the thermal sensation inside the room. And we have the force inlet fresh air flow and the force air removal and the other which is from the inside the CR or the washroom exhaust vent grill. So in this flow simulation, we will be able to also determine the estimate ventilation system effectiveness by using the CRE or contaminant removal effectiveness and lean air quality index. This one, SolidWorks will provide you this value. So first, as discussed, we will open the hospital room. Then let's make our SolidWorks flow simulation setup. So first is we have to define our project using a project wizard. Okay, so the parameters are current, use SI units, analysis is internal, the gravity is will be a factor for the simulation, and our default fluid will be air, and gases expired air will be user defined. So we will define it later. Then the wall condition is default, and the initial conditions of the room is about 19.5 degrees C. Mass fraction of air is 1 and mass fraction of expired air is 0. So our default resolution is 3. Okay, so let's set up first our flow simulation. So first is we have to go to wizard, click next, SI units as discussed, internal, then as per our example, should activate gravity and indicate the gravity at Y component 9.81. So Y negative because the arrow is pointing outward. So we have to make it downward. Gas is air, add, and we have to select a new one to make a new one. So and new. So gas user define air expired air. So new expired air. So let's see the value of the Okay, so we have to copy paste the air. So, okay, so I have to delete this one. So copy, user define, paste, then item properties, then expired air. Okay, then save. Alright, and then we have to add the expired air as I usually. Okay, unclick this one. Then next. So adiabatic walls, since we don't have interaction on the walls. Then let's go to the, click this one. So our temperature should be 19.5 degrees Celsius as stated in the manual. So in order to make this one, let's go to the units and change this one to Celsius. Then let's change the value 19.5. Alright, okay. So we already have so we have one problem that we encounter. So the model is still open, but one error that we did not do is have to suppress this one. So if you suppress this one, uh, the watertight error will be removed. Okay. Okay, so the default resolution of level 3 is already done. So you can access this in the global mesh, and you can see there's still 3 because that is the default value. Okay, so before moving forward, we have to click save all in order to preserve what you have done. Alright, okay, let's move on. So we have to specify our inlet volume flow, which is 4.8 cubic meter per minute. So we have to state that the air coming out from the vent from the duct is 4.8 cubic meter per minute, and on the outlet is 2.6. So let's start first. 4.8 cubic meter per minute. Boundary conditions, insert boundary conditions, right click, select other. So since we have to select inlet velocity, so the value is 4.8 cubic meter per minute. So this is 0 meters per second. So we have to convert it 4.8 cubic per minute. So let's okay, so let's continue. 4.8 cubic meter per minute. So it should be inlet volume, not inlet velocity. Then 4.8 cubic meter per minute is equal to 0.08 cubic meters per second. And the thermodynamic parameters are default. Okay. Then we'll go to outlet volume flow, which is 2.6 cubic meter per minute. Okay, so let's go to outlet volume flow, insert boundary conditions, volume flow. So select this one, and divided by 60. Okay, so let's input 0.04 cubic meters per second. Sorry, outlet volume flow. And for this one is environment pressure. So 100, 1325, and 19.5. So we have the second going out. So it's going out in the atmosphere. So it's the default thermodynamic parameters. So insert boundary conditions. So select environment pressure. Then select other. Right click, select other. Then the default thermodynamic parameters. So we have to just check this one. So we have the boundary conditions already set up. Okay. So we have the input and the outlet. Okay. For next setup, we have another one that is coming out from the mouth of the patient, which is inlet volume flow 2. So it's about 12 liters per minute. So according to this manual, there's a 12 liters per minute coming out from the mouth patient. Okay, so we have to indicate the substance concentration of mass fraction of air is 0, mass fraction expired air is 1. So let's set it up. So let's set it up. So let's go to the mouth, right click, insert boundary conditions, inlet volume flow, select the mouth, okay. Then the value is converted to cubic meters per second, 0.002. Okay, so we have the inlet volume flow. So let's go back. So let's check if we have input mass fraction of air 0 and mass fraction of expired air is 1. So using the model, okay. So now we will go to applying the heat sources. So we have different kinds or sources of heat in the simulation, from the ceiling lights, TV set, hospital equipment, and the caregiver and the patient. So first we have to set up the heat source for the patient and the caregiver. So first is click insert surface source. So click insert surface source. Then select in the flyout menu toolbar, select patient. So you can see all faces of the patient is selected, but we have to select the list all component faces. Okay, then go to filter, and since some of the faces are not in exposed because the patient is lying on the bed, so we have to select keep outer and fluid contacting faces only. So filter. So once done, we will go to how to we have to remove the face for the mouth because we have already selected this one. So and the heat transfer rate is about 81 watts. So let's input this one once we have the setup. 81 watts. Oops, sorry, forgot to remove the mouth as discussed. So we have already the setup there. So that's why we have an error. So I have to remove this and we have this setup. So the error is already gone. So it's good to know that I have did some mistakes in order to show to you that uh, those possible errors. So we need to rename this one patient. Okay, we need to add another for the caregiver. So for the caregiver, please select this one. And based on the manual, since there's no boundary condition specified, there's no need to exclude all phases. So just input 144 watts. Since nothing is underneath the bed or it's not lying on the bed or on the floor, the floor is not soft. So just indicate 144 watts. Then you're done. Patient 6. Oops. And have this another error. Why do I have this? Okay, sorry. So remove this one. So SolidWorks is a bit advanced. When you pre-select this one, it will already select this. So let's redo it. Insert surface source, caregiver, pass the value 144. Okay, I think we already got this. Okay, so let's rename it to caregiver. Okay, so we have already the caregiver and the patient. So let's set up the surface heat source. Ceiling lights. So the ceiling lights is about 120 watts. So let's select this one. Surface heat source. So insert surface heat source. So let's input 120 watts. Select other again. So those are the ceiling lights. 120 watts. So rename it. So you will not forget that value. Ceiling lights. And next is TV set. So we have to select the inner face of the room component, 50 watts. So where's the TV set? Here. Actually, you could do a cross section just to make our job easier. So we could access this one. So insert surface source. So the TV is generating 50 watts, and we don't need to select other anymore since we already uh, removed that. So we have to select the bottom part. So select other. Alright, so we already have that setup for the TV. Then another for the hospital equipment. The inner faces of the hospital, 50 watts again. So let's look for the hospital equipment. So you remove the top part using cross section for easy access. Insert surface source. So I don't need to do select other. Then 50 watts again. Oops, is the error? Okay, so since we have selected TV before, so let's delete this. The one that we did, because you know when you are selecting the faces, you already pre-select those faces for the TV. So hospital equip hospital equipment. All right. So we have the setup. So I will just bring this back again. Remove the cross section. Okay, once we have that one, we have to specify the calculation control options. So let's go to the calculate control options and go to the advanced, check calculate local mean average and calculate comfort parameters. Activate. So let's go check this one. So by the way, LMA is the average time for fluid to travel from the selected inlet to the point of considering both the velocity and diffusion, while local air change index is the ratio of volume over the Q, where V is the computational fluid domain and Q is the volume flow rate of the fluid entering this volume. Okay, so let's go to the calculation control options. Right click, calculate control options, solving, saving. So goals criteria, analysis, notifications, refinement, solving. So this one. So let's select additional calculate local mean age and calculate comfort parameters. For this version, there's no already calculate control uh, parameters. So yes, let's go by it. Okay, so since we are already using a different SolidWorks model, I'm using 2017. So the other tabs may not be already uh, available or is already incorporated to another tab. So let's specify our goals sa average mean radiant temperature, average operative temperature, average velocity, and average volume fraction expired. Then we'll set up the mesh. Okay, specify the goal. So right click on the goal, insert global goal. So average mean radiant temperature. So this is the beauty of search. Search the value. Average temperature. Average operative temperature. Have to select this one. Why is not showing the average temperature? Hmm. Okay, so before moving forward, I found some errors on the setup. So for this inlet volume flow, we forgot about stating the mass fractions. So I already put 0 and 1 as stated in the manual. So the substance concentrations did not display because on our general settings, I removed the check mark for the expired gas. So sorry for that. So I already updated that one. Okay, so for the goals as stated in the manual, so we have to select for the average volume of air. So let's go to this one. Average volume, fraction of expired air, and average velocity one. Average velocity. Okay, so I cannot select the mean operative temperature and the mean radiant temperature because I there's an error that I cannot find the calculation control options and activate the calculate comfort parameters. So it's maybe since 20 I am already using SolidWorks version, an updated SolidWorks version. So just for the matter of doing the simulations or illustrating, let's move forward. Then let's go to the initial mesh. So initial mesh is you have to indicate the gap size to 0.012. So input global mesh gap size to 0.012. This is so the patient mouse will be considered. Okay. To better resolve the complex geometry, so we have to create a local initial mesh. So in the feature design, select caregiver. Okay. Insert local initial mesh in. So insert local mesh. Then select caregiver and patient. Okay. Then go to solid fluids interface bar. Let's refine the fluid cells to 2 while small solid refine 2 4. Okay. So now we will run the calculation. During the calculation, you may notice the average volume expired lower than the other goal specified. Since this is the tutorial example, there may not be needed to wait for the solution to converge to save CPU time. You can stop the calculation earlier, for example, when all the other specified goals converge. So please take note of this. So we will run the calculation. Okay, so save. So once you set up, for my next video, we'll discuss about the results of the simulations. Okay, see ya.